Welcome back to Calculus 2, Section 3.7, Improper Integrals. We have a few different topics to go over. The first topic is integrating over an infinite interval. Infinity. Infinity is a paradoxical concept. Infinity is not a real number. In calculus, we are able to calculate with infinity thanks to the process of limits. This section is 3.7, improper integrals. When do we have an improper integral? Well, one case is when a bound, let's say the upper bound is infinity. Another case might be a lower bound being infinity, like negative infinity. Or a third case might be when both bounds are infinite. In all three of these cases, we are presented with an infinite interval as our domain of integration. When we look at definite integrals and interpret them as area under the curve, we can think of a base of a rectangle, for example, to approximate that area of some definite width. Here, having a base of an infinite width doesn't seem to lend itself to a definite area. So how do we tame this infinite base? We do so through limiting processes. So let's make that explicit. If we have an infinite interval which starts at a nice finite number and then starts heading towards the right, getting bigger and bigger, going out to positive infinity, we can define this, we can tame this infinite upper bound thanks to a limit. We can replace out that non-real number, the notion of infinity, with a placeholder, capital R. And then we'll be looking at definite integrals, which make perfectly good sense as area under the curve. And then let that placeholder tend out towards that notion of infinity. Taking a limit of this definite area, well, we have a definite area from A to R. What if we nudged this R a tiny bit more to the right? Then how much area would we have? Come up with a value. Oh, I see. And then repeat that process. Nudge this upper bound a little more to the right. Take a look at what you produce and repeat that process ad infinitum, which is the notion of taking a limit. Equally, if we have a lower bound, which is infinite, negative infinity, we can replace this concept of infinity with a definite value as a placeholder. The integral is then a definite integral, which we have a solid notion of. Let that lower bound become even lower. Take it more to the left. And consider what area is then defined. Let that process repeat ad infinitum. And if that area tends towards a definite value, then this right-hand side limit will exist as a finite number. And then we will have evaluated the improper integral with lower bound infinity. All right, so we're taming infinity through a limiting process. Very nice. This brings up a nice vocabulary word, converge. When that taming of infinity yields a finite value, we can describe that in this word converge. So, an improper integral is said to converge whenever the defining limit exists as a real number. Very good. So these two right-hand sides are how we interpret this left-hand side, improper integrals on the left, defined, interpreted as limits here on the right. When the limits on the right yield real numbers, then the improper integral converges to the value on the right. Nice. That's the notion of convergence. On the other hand, if convergence is not attained, then we can describe that situation with the word diverge. An improper integral is said to diverge whenever the defining limit does not exist as a real number. Very good. So here's what we've done. If we know that our integrand is continuous on the interval from a out to infinity, then the improper integral from a to infinity of the continuous f may be interpreted as the limit of a definite integral from a up to a placeholder, letting the placeholder go out to infinity, of the continuous f. Very nice. Let's do an example of that improper integral. Evaluate the definite integral from 0 to infinity. Integrand x. We know x is a nice continuous function. Restate the improper integral in terms of a limit. Swap out this non-real number x for a real number, placeholder r. Let r tend towards infinity. Very good. We've taken an improper integral, restated it as the limit of definite integrals. Now evaluate the definite integral. The integrand x has antiderivative x squared over 2. X squared over 2 at 0 is 0, and x squared over 2 at r gives you capital R squared over 2. Since we're letting r out to infinity, r squared will tend towards infinity. Infinity is not a real number. Thus, our improper integral, we say, diverges. Very good. Here's a picture of the limit of area under the curve y equal x. And that area tends to grow larger and larger and larger, which does not converge to a value. It is unbounded. Nice. Here's another improper integral for you to try. The improper integral with bounds 1 and infinity. Integrand 1 over x. Is this a convergent improper integral, or does it diverge? Very good. All right. On the other hand, we can consider a lower limit being infinity. This is also an improper integral, and we swap out with a placeholder and let that placeholder tend to negative infinity to determine the convergence or divergence. If, on the other hand, we have a function f to be continuous everywhere on the real line, we might want to consider the area underneath that curve over its entire domain. Note carefully that the way that we interpret this improper integral is that we choose to look at the area defined by negative inputs and add up the area defined by positive inputs. All right. So note carefully that the dividing point, that we break up this real number line at a natural location 0. And then also let's comment that the improper integral here on the left will diverge if either of the values on the right does not exist. So we might obtain divergence if this limit doesn't exist, or if this limit does not exist. Okay, let's do an example. Here our improper integral has bounds negative infinity and positive infinity. The integrand cosine of x is continuous over the entire real line. Let's break up this improper integral into a sum of improper integrals. And let's look at one of the improper integrals and notice again that by definition we choose 0 to be the breakup point. All right, so let's choose the negative inputs and see what type of area is produced. We have an improper integral. Let's change that into a limit of definite integrals. We swap out the infinite bound for a placeholder and let the placeholder tend towards that infinite quantity. Cosine of x has antiderivative sine of x. Sine at 0 is 0. And sine at r is sine at r. That's the lower bound, so it appears with a minus on it. Yet, when we take the limit of sine, as inputs tend towards negative infinity, sine, as a sine wave, oscillates up and down. It doesn't tend towards a fixed value. Thus, we know that this limit diverges. It does not exist. Hence, the improper integral diverges. Very good. So here are some examples for you to play around with. This integrand, 1 over 1 plus x squared, is continuous over the entire real line. This is an elementary integral. Use the definition of an improper integral with infinite lower and upper bounds to evaluate the integral. Investigate what would happen if you change the numerator from a constant 1 to the variable x. To evaluate this integral, first break it up into a sum of two limits and then investigate one of the limits through the use of u substitution. All right, and another one. This is an improper integral, and upper bound is infinite. And a final assignment. Here you want to go back and review using integrals to compute volume of solids of revolution. Set up the integral and notice that you'll have an improper integral as we want to consider a domain of integration from 1 to infinity. Nice. So this is the first of two ways in which we can encounter an improper integral where at least one of the bounds is infinite. A second way in which we can have an improper integral is when the integrand is discontinuous. Now, let's start off with a definition. Let's suppose that we have a function f, and that the function f is a nice function on an interval, closed on the left but open on the right. Then the definite integral from a to b, so here you want to notice that f at a is perfectly well defined, but our assumption that f may or may not be defined at b, as we're only assuming that the function is continuous on the interval closed at a but open at b. Well, we do not need to have any further information about the behavior of f at b. We're saying that this definite integral will be obtained by a limit of definite integrals where that placeholder moves up towards b. Good. Likewise, if we have only information of f being continuous on the interval open at a and closed at b, that this definite integral can be evaluated in the limit of definite integrals where the lower bound will tend towards down to a. Okay, so let's do an example. Our integrand, 1 over the radical of x. If you just look at radical of x, it's defined from 0 to 1. However, radical of x is appearing in the denominator. Thus, 1 over rad x is defined everywhere except at 0. And in this instance, 1 over rad x will tend to blow up as x's tend towards 0. So whereas our first instance of improper integrals was dealing with an infinite base, in this instance of discontinuity, we're equally obtaining an improper integral as heights are tending towards infinity. Okay. Now, let's go ahead and rewrite our improper integral as a limit. So, again, we cannot divide by 0. So we swap out that lower bound for a placeholder, and then let the placeholder tend from one side to the value. So this is a limit from above, and we've rewritten 1 over radical x as x to the negative 1/2. Good. Go ahead and do a computation. Negative 1/2 increments up to positive 1/2. That's x to the 1/2. And the reciprocal of 1/2 is 2. Plug in the bounds. Get 2 as a constant brought to the front. Radical of 1 is 1, and the radical of r is rad r. But r is tending down towards 0. So the radical of r in the limit is 0. 2 times 1 is 2, and that is our answer. So even though as the dummy variable x tends to the lower limit, and the heights of the rectangles in the Riemann sum tend to have infinite heights, this improper integral in the limit tends towards 2, a finite value. Very good. Okay, so we have discontinuity occurring at an endpoint. Equally, we could be presented with a definite integral where the function is defined and continuous at endpoints However, at some point on the interior between a and b, the function might be discontinuous. So suppose that at c we have a function f which is discontinuous. The way that we handle an improper integral with discontinuity at some point c between a and b is that we separate out and write our improper integral as a sum of two improper integrals. So we use the dividing point c, and then consider whether each of these improper integrals is convergent or divergent. If both are convergent, then our original improper integral converges. If either improper integral is divergent, then the original improper integral is divergent. Let's do an example. So, tangent of x is our integrand. Think about the graph of tangent of x. You know that tangent of x is asymptotic with the vertical line. X equals pi over 2. Pi over 2 is a value that sits between 0 and pi. And tan is not even defined at pi over 2. So we want to consider breaking up this improper integral into two separate improper integrals, where the dividing point is that point of discontinuity, pi over 2. So we consider the improper integral from 0 to pi over 2. Tangent blows up at pi over 2. Tangent on the other side of pi over 2 is tending towards negative infinity. And then let's investigate these integrals. Let's try the integral from 0 to pi over 2. That's an improper integral since tan at pi over 2 is not defined. We swap out that discontinuous upper bound with a placeholder r, where r is smaller than pi over 2, and then we let r tend up towards pi over 2. We know that tangent has antiderivative, the natural log of the absolute value of secant. As the r value tends up towards pi over 2, secant will tend towards infinity, and the natural log of something tending towards infinity is infinity. Thus, this quantity does not exist as a real number, and our original improper integral diverges. So we've established that this improper integral on the right diverges, and that's enough to conclude that the original improper integral diverges. Good. Your turn. Here's what seems to be a plain vanilla definite integral, but on inspection we know that 2 resides between 1 and 3, and plugging in 2 into the bottom would lead to division by 0. Thus, this is an improper integral. Very good. So we've gone over to the two cases. Maybe the base is infinite, or maybe the height is infinite. Those are the two ways in which an integral may be viewed as an improper integral. Next, let's use our understanding of improper integrals to come up with a comparison theorem. All right, let's describe what we're looking at here. We have a red graph and we have a blue graph. We've named the red graph the graph of G and the blue graph the graph of F. And we've taken the F and the G such that at any point x, the F is producing a value less than or equal to the value of G. Good. Now note, if we were to consider integrating f from some point to some point, that we would produce an area And if we use those same inputs, bounds of integration, on G, that the area under G, as G is a larger integrand, would be greater. On the other hand, if we considered G's, integrating G, that the amount of area that we produce would be a greater value than the amount of area produced integrating F. Pretty straightforward notions. Well, let's take that one step further. Let's have F and G be continuous from some definite value out to infinity, and assume that the relation between F and F continues, that F is always less than or equal to G, and that both of these are positive functions, or non-negative functions. Then two conclusions may be drawn. If we take the integral of F from some a value out to infinity, and if we come up with this being a divergent integral, then these small quantities in the limit are tending to infinity, are tending to blow up. Therefore, the area under the G, which is always bigger, will also tend out towards infinity. So that's the first of two statements that we can make. If we focus on the small, and the small tends to add up to be infinitely large, that's going to imply that the larger is also blowing up. Let's flip that around. Let's look at the larger quantity, the area under the curve of G, and if in the limit these quantities tend to some finite value, then that's going to imply that the area under the F's, which are all smaller than the corresponding areas under the G's, will also be controlled and tend to some limit L. Moreover, that limit L will be no bigger than the limit M. Okay, let's make both of those statements together. So we have non-negative F and G, such that the F is less than or equal to the G. If you focus on the improper integral for the F's, those are small quantities, and even the small quantities sum up to something infinite, then trying to sum up the large quantities is going to give you something infinite. Flip that around. If instead you consider the large quantities, and those large quantities, when you add them all up, you produce some finite value, then when you go and you look at adding up all the small quantities, two things are going to happen. That those small quantities will tend to a limit, will also converge, but moreover, the quantity it converges to will be no bigger than the convergent quantity of the larger G's. Excellent. So this is a comparison theorem for divergence. And this concept will pop up in a later chapter and be a central idea to the course. Fantastic. Let's do an example. Okay, so here we have an f. The f is an exponential, e to some power. And then the g, remember that the exponential is always non-negative. The g is you take that same exponential, but you multiply it by x, and we're assuming x's are bigger than 1. So bigger than or equal to 1, multiplying f is going to produce a larger value. In other words, f's are non-negative as an exponential, and then g is x times that non-negative, and x is bigger than or equal to 1, so g will be bigger than f. Good. Now, You'll be asked to verify that this improper integral of g is 1 over 2e. What do you know about 1 over 2e? It's finite. So our comparison theorem for divergence, well, we're finding that the large quantities sum up to something finite. That's going to force the smaller quantities to also sum up to something finite. And in particular, they sum up to something less than or equal 1 over 2e. Good. So verify that this improper integral converges to the value 1 over 2e. And lastly, consider the function f of x as 1 over x, the function g of x to be ln of x over x. Use x's to be greater than or equal to e, and then show that the improper integral of g from e out to infinity diverges. So here you'll want to first integrate f over this same domain, e out to infinity, show that that improper integral diverges, and then appeal to the comparison theorem to say that the integral of g over the same interval also diverges. Fantastic. That brings us to the end of this video. Thank you so much for watching. Please like if you find this video useful, and I will see you on the next one.